Today let us continue from where we were discussing the queuing theory concepts. So far we have discussed the basic necessity that why queuing networks are required, and thereafter we have seen the birth and death process, the different types of queuing examples related to the distributions like exponential and Poisson distribution, and thereafter we also solved problems related to let us say mostly the MM1 type of queues, but one problem we have also solved for multiple servers. Now today let us look further into two categories of queuing systems, particularly multiple servers MMS and a special case of the multiple servers which can be called the infinite servers or the self-service model. Now already these equations we have seen in our previous class, that when there are multiple servers, then the formula are little involved, and however not difficult to compute, only thing the formula is a little bit we need to remember, but other than that this formula see, but again there are only two things which one need to recall. One is the value for P0, that formula is given here, that is the very first one, and the formula for LQ, right. So, once a person knows the probability of 0 persons in the system, that is P0, and also the formula for LQ, that is the expected number in the queue, using these two formula one can find all the other formula by using the Little's formula. WQ LQ by lambda, WQ plus 1 by mu, and L lambda W, that is lambda WQ plus 1 by mu. But one thing must be remembered here, that the utilization factor in this case is not lambda by mu, but lambda by S mu. So, this factor has to be remembered very clearly. So, some books you will find which will say rho equal to lambda by mu, is all right, but in that case that rho is not utilization factor. The way we have used rho here, it is taken from the Hillier-Lieberman's book, and rho is used as lambda by S mu, which is utilization factor. Those books which writes lambda by mu equal to rho, they just substitute lambda by mu by that factor, and they do not mean rho by utilization factor. So, it should also be remembered therefore, particularly the LQ formula, where it is written lambda by mu to the power S rho by factorial S 1 minus rho whole square P0, that rho is nothing but the utilization factor, that is lambda by S mu. So, this fact has to be remembered very carefully. Now, a problem that we had already solved about a small bank that has two counters, one for deposit, another for withdrawal, and arrival in both is Poisson process at 10 per hour, and while the service is 10 per hour for deposit and 20 per hour for withdrawal, and exponentially distributed service time is 2 minutes per customer for each of the counters. So, usually for such problems we like to know the average waiting time in the system for the both counters, and we have already solved this problem for MM1. So, you see this is the first case where we think that this is my deposit counter, there is a queue formed in front of deposit counter, there is an withdrawal counter, the queue formed in front of the withdrawal counter. So, these two are separate processes, and for these separate processes we already found that for this one lambda is 10 per hour and mu is 30 per hour. So, we had rho equal to 1 by 3, we had L equal to rho by 1 minus rho equal to half, and we also have W equal to L by lambda, which has come up to be, because lambda is 10, 1 by 20 hour, that is equal to 3 minutes. So, this we had seen already for the deposit counter, and for the other counter this is 20 per hour, mu equal to 30 per hour, rho equal to 2 by 3, L equal to rho by 1 minus rho equal to 2 by 3 by 1 by 3 equal to 2, and W equal to L by lambda equal to 2 by 20 equal to 1 by 10 hour equal to 6 minutes. So, these calculations we had already done, and this is available to us in our previous lecture, but just repeated here. But one thing must remember, that these are 2 mm1 queues, right. Now, when we use what is known as an mm2 queue, what exactly we do? We do combine the two, and we have a system which is an mm2 queue. How are we getting this mm2 queue from the 2 mm1 queue? Is a process what is known as pooling of resources, right. What is the pooling of resources? Now, there is a server system, there it is, and each can do deposit plus withdrawal, right. So, these are the two counters, and both can do deposit as well as withdrawal. Now, question is, this is something a very tricky question. How is are there two different queues in front of the two counters, or there is a single queue? You see, as far as literature goes, we assume that there is a single queue, but what is the difference between this process and let us say another process? Just think about this. These are the two counters, there are two different queues in front of the two, but both can do both. This is also can do deposit plus withdrawal, and both the counters can do deposit plus withdrawals. What is the difference between these two? You see, what happened in this particular case, that suppose one of the queue is empty, then will the person keep waiting here? I mean will the other people who are waiting in a long queue in the other counter, they will simply come here and get their service. So, in a way, as if there are a single queue only thing, the queue discipline may be different, because you see the things are different as far as an individual customer is concerned. Here the person knows that so many people are before me, but here this person knows only one person is before me, and I can get my service once the previous service is over. So, there is a difference from the customer's point of view, but as you remember, already I have told that the performance variable values, steady state performance variable values, what are some performance variable values? The L, LQ, W, WQ, they are independent of queue discipline. What kind of queue discipline? The kind of queue discipline that just does not affect the process. Now, these queue disciplines like FCFS, Syro service in random order and last in first out. This kind of systems, they don't or they do not what is known as they are not changing the system input or service processes. Therefore, those performance variable values are independent of queue discipline. So, under those situations that these LLQ and WWQ values, they are not going to change, right, depending on whether they are standing in two different queues or a single queue. Only thing it will make a difference in the service of individual person. More about that later, but let us see what happens with pooling of resources. Look at this slide. Here this P0 formula, that will be given by this lambda by mu to the power n factorial n, lambda by mu s and factorial s, and 1 by lambda by s mu to the power minus 1. And this P0, in our previous class we have seen that this P0 comes out to be 1 by 3, right. And what is the lambda here? The lambda will be equal to the two processes 10 plus 20, that is equal to 30. The mu remains at 30 per hour, and what will be rho? Rho will be lambda by 2 mu. Why 2 mu? Because there are two servers. So, in this case, lambda by 2 mu. So, this lambda is 30 and this will become 60. So, rho will be half. So, in this case P0 comes out to be 1 by 3, that calculation I have not shown here, but it will become 1 by 3 and rho equal to half. And the computation of LQ using the formula, that also comes out to be 1 by 3 hour, right, no sorry not hour, 1 by 3, and W really comes out to be 1 by 3 into 60, that is because W is L by lambda, lambda is 30. So, equal to 1 by 90 equal to how much? It comes to be WQ is 1 by 90. So, again we have to find, this is WQ, W equal to WQ plus 1 by mu equal to 2 by 45, right, and that comes to 2.67 minutes. Once again, lambda is 30, mu is also 30, P0 is 1 by 3, rho is half, LQ comes out to be 1 by 3. From LQ we can find WQ by dividing LQ by lambda. So, it get 1 by 90, and W, then WQ plus 1 by mu, that is 1 by 90 plus 1 by 30 comes out to be 2 by 45, which is 2.67 minutes, right. So, what is really happening, that you see when the services were separate, then one was taking 3 minutes and the other was taking 6 minutes, right. And when you combine them into a single MM2 queue, then we had the the W comes out to be 2.67 minutes. That means average waiting time in the system reduces for both the counters. And why it happens? It really happens because you see, when a deposit counter is free, right, but the withdrawal counter is very busy because there are a lot of people waiting there, this free counter is not helping those people who are waiting in front of the withdrawal counter, it does not help them, right. So, but when what happens in the pooling, since both the people can do deposit as well as withdrawal, no counter will remain free as long as there are customers. So, this will reduce the free period of individual counters, and pool the resources in that sense and show better performance. So, that is what is the advantage of pooling of resources. That creates improvements in the system performance. This is because when the two counters are not pooled, one counter may be idle while the other is busy. The work goes on at a rate equivalent to only one counter. With pooling, when there are no deposit customers, both counters can carry out withdrawal work, thus increasing efficiency. So, what pooling of resource really help in achieving? It helps in, first of all, balanced utilization. The utilization of both the counters are possible, and it does not happen that if, see, usually what will happen, deposit counter only 10 per hour is the arrival, withdrawal counter it is 20 per hour. So, therefore, the deposit counter may remain free most of the time, and whereas withdrawal counter will be busy all the time. But if both can do both, then the load will be divided and both will be working, and therefore, the performance of both are going to improve, right. So, that is the advantage that we get with pooling of resources. The waiting time reduces, the second one, shorter waiting time, and finally, also the ease of customer operation. You remember in the earlier days when we used to buy railway tickets, and there used to be counters which used to give only daily tickets, other counters will give something like Madras tickets or Chennai tickets. You have to really wait in a particular counter for long time, but you have to know what is the specific counter where you have to go, and assume, suppose you have to go to 5 directions and there are 5 different counters, how difficult it is. But today you can join any queue, right. There are 5 counters, join any of the 5 counters really and get your ticket. So, that is the advantage of pooling of resources, balanced utilization, shorter waiting time and ease of customer operation. A special case on this, which is called the infinity or the self-service model. You see, this is an extension of the multiple server model, where number of servers are infinite. Then what does it mean? It really means that nobody will going to wait, right. There is no question of wait. You come to the bank and there are infinite number of counters, join any one of them, right. So, it basically what? It is like a self-service. It is like a self-service. So, when the self-service facility is available, it is very clear that there is no expected number in the queue. So, you can see LQ equal to 0, right, and also WQ will also be equal to 0, right. So, it becomes almost like a Poisson process, and therefore, we find that L will become lambda by mu. Lambda is the arrival rate, mu is the service rate. I will not go into the derivations, but the formula for P0 will become e to the power minus lambda mu, right, and other probabilities will be e to the power minus a stands for lambda by mu, a to the power n, that is e to the power minus lambda by mu, a to the power lambda by mu by factorial n. So, it is a Poisson process, right, and what will be the waiting time? Waiting time will be 1 by mu. So, that will be the difference in the formula, very simple formula really. Their LQ and WQ both are 0, W equal to 1 by mu, L equal to lambda by mu. That is what happens in a self-service process. So, for the same example, you see what will happen in the self-service situation. The self-service situation, in this case, supposing this is our infinity q, let us write that also, infinity q. We have already seen what is known as the 2 1 q's, 2 q, and suppose we have now infinity q. In this case, the lambda equal to 30 per hour, mu is also 30 per hour, right, and the service system is like an infinite queue. Any customer, see, virtually there is if I really draw a picture, in this picture there are like infinite servers. The customers can do virtually there is nobody waiting, everyone is, as they come they get a separate place to really get their work done. So, what will be W in this case? The W formula already known is 1 by mu, right, and that is 1 by 30, that is equal to 2 minutes. So, look here how it changes. When we had two different counters, we had waiting time equal to 3 minutes and 6 minutes. When we pooled the resources and made it MM2, right, Q, at that time we had the W becomes 2.67 minutes, and really if you can make it self service, right, like something like you do it yourself on your computer, right, don't even come to bank, and suppose it just takes 2 minutes to do one service, then waiting time becomes simply 2 minutes, because that is the time you spend in getting the job done, right. Service time is how much? 2 minutes, and that is the waiting time also, because there is no queue, nobody waits in the queue. So, it is very simple, W becomes 2 minutes. So, how do they compare? Here is a comparison chart, just look what happens between MM1 deposit, MM1 withdrawal, MM2 and finally MM infinity self service. So, let us look at all these. The arrival rate is 10 per hour, 30 per hour, 20 per hour and 30 per hour, 30 here also 30. Now, P0 formula, this becomes 2 by 3, this becomes 1 by 3, because P0 is 1 minus rho is 1 by 3. So, P0 is 2 by 3, this is 0.333 and this is 0.368. How this 0.368 is obtained? Just look, P0 e to the power minus lambda by mu e to the power minus 1, that is 0.368, lambda by mu is equal to 1, right. So, you can see that this formula for P0 really shows that the system is busy period is maximum, right. So, no, this is something wrong, this should be 0.632, 63.2%, that is the busy period. Yeah, this is something wrong, and whereas the other cases, so it is not busy that much, but since how this thing is compensated really is by this infinite number of servers, because there are more servers, there is no waiting time, that is how it is compensated. But one more interesting thing, let us look at this MM2Q. The MM2Q, the P0 is 0.333, but busy period is 0.667, is it not? So, but what was the let us go back and quickly see what was the value of P0. P0 is 1 by 3, P0 is 1 by 3 and the value of lambda is half, that is value of rho, system utilization factor rho is lambda by S mu, that is half. So, system utilization is 50%, right. So, 50% time the system is not utilized fully, but what is the busy period for MM2 is 66.7%. So, how does it account for the remaining 16.7%? What is the really how this gap will be bridged? This gap, because see here rho lambda by S mu, which is half, because lambda is 30, mu is 30. So, 30 by 60, S is 2, 30 by 60, that the utilization is only 50%, but how the system is busy is 66.7%, where this remaining 16.7% came. We have to understand that this gap is really coming from the consideration that while one counter is busy, other could be idle, right. So, when it comes to utilization, then this utilization is becoming half, right, at that time. So, the case could be both are busy, both are free, one is busy, other one is busy. So, when only one of the servers out of the two are busy for those periods, right, the utilization is really not full. So, that is the difference. That is why the busy period could be 66.7%, that means at least one counter is busy. However, the utilization is only 50%. So, that point must be remembered. Look at another example. In a small city, there are two identical cab companies. For each, the arrival rate of customer is 4 per hour and average service time is 12 minutes. Assuming Poisson arrival and exponential service time distribution, find out whether there will be a change in the utilization factor rho or waiting time in the queue WQ if the two companies merge. You see, there are two separate cab companies, right? Customers call to each at 4 per hour and their service time is 12 minutes. So, what happens when they operate individually and what happens when they pool their resources and serve as one company. So, the first thing is rather easy, that without pooling the lambda is 4, mu is 5, the utilization is 80% and LQ rho square by 1 minus rho is 16 by 5 and therefore, average waiting time WQ comes out to be LQ by lambda is 16 by 20 equal to 48 minutes, right. So, look here, without pooling it takes 48 minutes for a person to wait in the queue before the person gets a cab service. What happens if we pool the resources? When we pool the resources, then lambda becomes 8, service still becomes 5, the system utilization factor is lambda by S mu becomes 80%. Using the MM2 queuing formula, lambda by mu to the power n by factorial n, lambda by mu to the power s by factorial s and 1 by 1 minus rho inverse, that inverse must be remembered. So, when you compute this we get 1 by 9 and then the LQ formula shows LQ is 128 by 45. So, WQ will be 128 by 45 divided by 1 by 8, I mean 8. So, gets 128 by 360, right, that is 16 by 45 hour or 21.33 minutes. So, what happens, utilization at 80%, but WQ reduces from 48 minutes to 21.33 minutes. So, that is the kind of advantage one can get out of pooling of resources. And what happens in self-service? The WQ is 0 because nobody waits. Look how the problem changes. The company gives cabs for customers to ride on their own for a fee, and but then there is no constraint on number of vehicles available, because that is the constraint. So, really it is not really possible to have an infinite self-service facility. Arrival rate of customers is 8 per hour and average service time is 12 minutes. So, what will happen? What will really happen is the P0 is 20.2% and the busy period becomes 79.8% and average waiting time is 0, right. So, how do they compare? The arrival rate 4 per hour, 8 per hour, 8 per hour, service rate 5 per hour in all the three cases, P0 20%, 11.1% and 20.2%, busy period 80%, 88.9% and 79.8%, WQ 48 minutes, 21.333 minutes and 0 minutes. So, that is really shows the comparison that if the two companies really merge and really serve together, they can definitely give a much better service, because when one is free the other may be utilized. So, they can take the load of the other one during their free period, and that is how the pooling of resources happens. And that is why, if you really improve queuing system, it is imperative that we pool the resources and try to make a multiple server system out of several single server systems. Thank you very much.